So welcome everyone for our third talk, our safety seminar this year. So this time we will have a guest speaker, Chong You from Google NYC. Dr. Chong You is graduated from Johns Hopkins with Professor René Vidal, and he afterwards he did a postdoc at UC Berkeley with Professor Eva, and his research interests mostly in he used to work on sparse substrate clustering. He did very interesting work on sparse substrate clustering during his PhD work. And during his postdoc, he did lots of interesting work on deep neural understanding of deep neural networks. So in the talk, he will tell us more of his recent work on robust learning of deep neural networks. So let's welcome Dr. Chong You.
Hey, thanks, Tim, for the introduction. It's really a great pleasure to be here to give a talk on our recent work. So the title of the talk is Robust Learning via Double Over-Parameterization. So basically, double over-parameterization is going to be the method that I'm going to talk about. So let's get started. So one of the most important trends with machine learning during the past decade is that we are training models with larger and larger scale, right? So here I'm showing one figure, but you've perhaps seen many figures like this, where if we plot the accuracy of the model on the y-axis, and then the scale are measured by the number of parameters in the x-axis, then we're going to get a curve like this, where basically it's a going upward, right? So as long as you push forward on the scale of the model, you constantly get better and better performance. And in fact, during the past few years, the size of the model that we are able to train has grown by several orders of magnitude. But still, up until today, we are still seeing this trend, right? Where this trend of going upward is yet to plateau. And in fact, a lot of the research efforts these days are still about how we can train even larger models, right, beyond what is listed here for the purpose of getting better performance. And in fact, large-scale models are getting a lot of attention, and there is actually a word to describe them, and that is called over-parameterization, right? And so basically, that term just means that you have too many parameters. That the number of parameters is even larger than the number of data points, right? Which is captured by this inequality here. So the 23 million is the number of parameters in the ResNet 50, and then 1 million is the ImageNet, the size of the ImageNet data set on which this ResNet 50 is trained, right? And the immediate implication of over-parameterization is that our network is so powerful that it is able to fit any training data, right? Not necessarily the clean data like ImageNet, but even if you have like noisy data or even random data or random label, you can still fit that data, right? And therefore, while large-scale over-parameterization brought a lot of the benefits for getting better and better performance, it also brings a lot of the challenges, right? And one of such challenges is their lack of robustness. So what I'm showing here is a kind of a very famous figure from several years ago on evaluating the performance of machine learning deep learning models for data sets with corrupted training labels, right? So in here, the x-axis is the percentage of the corrupted labels in a training data set, and the y-axis is the test type. So what we can see here is that when the percentage of corruption is small or zero, then we get a pretty decent accuracy, right? In particular, with the inception network, we get around 10% error. But as long as we increase the amount of label noise by a little bit amount, then suddenly the performance drop very rapidly. Okay. And why is that happening? So here we conducted a little of the experiments to look into learning curves to see what's happening, right?
Change the zoom, sorry, so that Zoom can see your slides. Oh, never mind.
That's okay. Yes, I can see you.
Okay.
All right, great. All right, so I was saying, so here this is the learning curve for training a neural network on CEFR10 with 40% label noise on the training data, right? And here the solid curve is the training curve. And we can see that if you train all the way until the end, you get 100% training accuracy. But that is not what we want in this case, right? Why is that? Because 40% of the label are wrong, right? And obtaining 100% training accuracy means that our model is memorizing those 40% wrong labels, right? Which is not what we desire. And to demonstrate that, right, we can look at the test curve. It's showing a trend where the performance first increase, like here, right, on the dotted curve, and then after a while it starts to, performance starts to decrease, which is showing a sign of overfitting. Okay, so to illustrate what we are able to achieve at the end of the talk, right? Our results, the result of our method is illustrated by this green curve, where in terms of training, right, our method doesn't get to 100% training accuracy. And in fact, in this case, it's getting to around 60% training accuracy, presumably because it's only or primarily fitting the clean label, but rather than the wrong labels, right? And correspondingly, in terms of the evaluation accuracy demonstrated by the green dotted curve, we don't see this sign of overfitting. The training accuracy just continue to improve all the way until the end. Okay, so that's what we are gonna achieve. So, okay, so before we talk about how we achieve that, right? So let me, please allow me to introduce to you a little bit of the history of robust learning, because, this issue of robustness, right, is really kind of a eternal issue in engineering practices, right? It's not only an issue within the scope of deep learning, and it's even not only in the scope of machine learning, right? And even around half a century ago, when people were studying signal processing, there's already this issue of robustness, right, or corruptions in the data. So here I'm listing this example of recovering a band-limited signal from corrupted measurements, right? So here the Y on the top is our observation, but it's the noisy version. So it can be decomposed into two parts: the clean part, the clean low, band-limited part, and the sparse part. So here the problem is that we only have access to Y, and how can we recover the underlying band-limited signal, right? And this problem may appear to be challenging because we are trying to obtain two signals from one, right? But it turns out that this problem is actually tractable by using a very simple algorithm, and that is shown at the bottom here, right? All that we need to do is to solve this optimization problem where we find a theta that is closest to my observation Y, measured by the R1 norm, right? So here I'm using R1 norm because the noise is sparse. Okay, subject to the constraint that theta is a band-limited signal. So that's all we need to do. And not only is this method very simple, at least conceptually, right? But also it comes with theoretical guarantees. And this is a kind of a very old result from 1965, right? So by and large, so here is kind of an informal statement. By and large, it's saying that as long as certain incoherent condition is satisfied, then you're good to go. This simple program shown here at the bottom is going to give you correct solution to the problem on the top, right? And what is this incoherent condition? By and large, it's saying that the band-limited signal should be band-limited enough. It shouldn't be sparse, and the sparse signal should be sparse enough. It shouldn't be band-limited, right? Otherwise, there is no way they can be decoupled. And then this kind of result is perhaps more well-known in the context of a compressive sensing, right? And here, this is actually work in 20 years ago. Yes, and here the problem, we can phrase that as that we have a subspace and we have signal that is on this subspace, but we don't directly observe the signal. And what we do observe is a sparsely corrupted version of that one. And the question is, how can we recover that signal? So here, again, the same method shown at the bottom is going to work, right? So all we need to do is to minimize the L1 norm, subject to the appropriate constraint in here. And also, again, we have these kind of nice theoretical guarantees, right? As long as certain incoherent condition is satisfied, then you're good to go. And finally, this kind of results were also introduced to the community of machine learning, right? This is around 10 years ago for the problem of robust principal component analysis, right? So here the signal becomes the Laurent matrix and the corruption is still sparse. And then the method is still the same or roughly the same as before, right? You solve this optimization problem where you minimize the R1 norm subject to certain Laurent constraint or regularization. And then again, here is this nice theoretical results showing that as long as you get certain incoherence between the Laurent component and the sparse component, then you're good to go. You're guaranteed to correctly recover the Laurent matrices. Okay, so we really have this classical robust learning technique that is conceptually very simple and also comes with theoretical guarantees, right? And what's more, it also performs well in practice, right? So here what I'm doing is to, so I actually here did some experiments with the Laurent matrix recovery problem, which is the last one in the previous slide. And here the x-axis is the percentage of sparse corruptions that are injected, and the y-axis is the recovery error for the Laurent signal, right? So what we desire is the zero recovery error, right? So the message here is that you see, as long as my percentage of corruption is below 40%, right? And then we are able to obtain perfect recovery, right? So which is kind of saying that, it's kind of a surprising result somewhat, right? Like you can achieve actually perfect recovery as long as you are not overly corrupted. And if this is not surprising to you, let's contrast this to what we have seen, right? In this figure for deep learning with label noise, right? If you inject only a little bit, 10% or 20%, you have a drastic decrease in the performance, right? So that's the kind of the power of this kind of classical approach. Okay, so now what we have this classical approach that is again simple, comes with theoretical guarantees and also work very well in practice. So now problem solved, right? Why is that? All that we need to do is to formulate our label noise problem into the form that we are already familiar with, right? And then just apply our method. Can it be formulated in the way that we're familiar with? Yes. Why is that? So suppose that this yi is our noisy label or the observed label that is probably noisy, right? It can be decomposed into the summation of these two parts. The first part is in some sense the clean signal, right? So here the theta star is kind of the oracle parameter. And what I mean by oracle parameter is that you can consider that as the parameter that you obtain from training without label noise, right? Or from training with clean data. So that's kind of the desired parameter you want. And then the second term is just the label noise term, that which is the difference between the clean label and the observed label, right? So we do have this kind of decomposition, and then why not just apply the method we know about, right? All we need to do is to solve this problem with R1 minimization, right? So we need to, find a theta that minimizes its distance to the observed y measured by the R1 norm. Then you should be able to do the trick, right? But the reality is no, right? And it's actually pretty easy to see. And the reason that it's not going to do the trick is precisely because the model or the deep neural network is over-parameterized, right? And here we can actually establish a rigorous argument, right? The argument is that all the global solutions to this optimization problem are going to be overfitting solutions. Why is that? So first of all, this is the sum of the R1 norm. So the objective, the optimal objective value is lower bounded by 0, right? Second, that global optimum is going to be obtained if and only if this equality holds, right, for all the 0 points, right? So, which is, and this is not what we want, right? This is the overfitting solution. This is saying that neural network produces the noisy label, the corrupted label, not the clean ones, right? So this is the overfitting solution, which is saying that this method is not really going to work. For, at least for this kind of over-parameterized models, right? So now the question is, what do we do, right? So option number one, we just throw away all the, the nice method with simple methods and theoretical guarantees, all those stuff. We throw those away and start from scratch to build something new. And another idea is to see, okay, so since we've learned a lot about these nice methods, is there a way to revamp the methods so that they can be adapted to modern over-parameterized models, right? And in this talk, I'm gonna take the second approach, right? Let's try to revamp this classical method to develop something new. And through the process, we're going to see how the new method that I'm going to develop is, intricately connected to this classical method that I've just talked about. Okay. Okay. So as I outline the talk, so I'm going to talk about our method in the context of over-parameterized learning for 3 tasks. So the first task is robust image classification under label noise, which is the running example that I've been using. And the second task is the task of robust image recovery. And the third one is robust matrix recovery. And then we're gonna draw the conclusion at the end. Any questions up to this point? Okay, so so let's start with talking about this work on robust training under label noise by over-parameterization. And this is joint work with Chong You at New York University, with Zhihui Zhu at Denver University, and with Qing, who is sitting here. And this is work that was accepted to SCML this year. Okay, so so I'm gonna since our method is very simple, I'm just gonna directly throw at you how our method works, right? So this is basically the main formulation of our method for addressing the issue of label noise. Okay, so here I'm having this long formulation, but if we cover this yellow term here, then it is just the regular training pipeline that you use for image classification, right? Where this F is your neural network, Xi is your input image, and theta is the learning parameter of the network. And then Yi is the corresponding label encoded by a one-hot vector, right? So that's and then you're minimizing the cross entropy loss. And that's the thing that you want to optimize. Sorry, give me 1 second. Okay, so what's the idea here? So the idea here is that we want to introduce this new term called the sparse over-parameterization term, this yellow term. So what's the goal here? The goal here is very simple, right? What we want to achieve is that, since we know that this noisy label Y can be decomposed into the summation of 2 parts, the clean part and the noisy part and the label noise part, what we want is that we want the first term with this theta to converge to this oracle neural network that produces the clean labels. And then we want the new term, the yellow term, to converge to our label noise, which is the difference between the clean label and the corrupted label, right? And that's it, right? That's the idea. Okay, so that's the idea, but is that going to work, right? And if you look at it, then it seems to make sense, right? Why is that? Because this is actually a global solution to this optimization on the top, right? Because here again, we are minimizing the summation of CE loss, which is lower bounded by 0. And then if we have F equals to this F theta star and the yellow term equals to this I star, then it's going to give us 0 objective value, right? Which is showing that this is the desired solution is really a global solution, right? So at least from an optimization perspective, this seems to make sense, right? All we need to do is to solve the problem on the top, right? But at this point, maybe it's a good point to recap, right? Because something is wrong, right? And at the beginning of the talk, I was saying that we are working with over-parameterized models, and because there are too many parameters, the drawback is that we're overfitting, right? Because of the over-parameterization. So here, how am I proposing to address the issue? I'm proposing to introduce even more parameters, right? And here, basically, for each data point, you introduce a UI and a VI. So that's a lot of parameters, right? So how come that introducing even more parameters upon a over-parameterized system can help to address the overfitting problem, right? So that's something is wrong, right? And what is going wrong here is that well, this desired solution is one global solution, right, to this optimization problem, it is not the only one, right? And in fact, there are infinitely many global solutions, and not all of them are the desired ones. And it's actually very easy to construct such an example, right? Let's say we consider this example where ui equals to vi equals to 0 for all the I, and this network just produces the noisy label. So that is also a global solution, right? You just plug it in, it gives you 0 cross entropy. But that is not a solution we want because it's, again, overfitting to the noisy labels, right? Okay, so then what do we do? So that's the challenge now, right? And our idea here is very simple, right? The idea here is to say, okay, I have a formulation that has infinitely many global solutions, but here is represented by this blue curve here. Yeah, what's the question?
Could you explain the new terms you're introducing, the intuition?
Yeah, I guess the question is, why do I have to have this term to be in this specific form with this old Hadamard inner product, right?
And what are the dimensions of the various terms and so forth?
Yeah. So so first of all, this yi is the one hot vector. So it's the dimension of yi is the number of classes, and so is f. And therefore, all the ui's and vi's are of the same dimension. Yeah.
Why you need the difference?
So again, what's the concept?
What's the what?
What's the concept behind this particular form?
Yeah, that's a good question. So that's a question that I'm gonna provide an answer in 2 slides. Okay, so yeah, you're totally right. From this perspective of obtaining this goal, all we need to do is to introduce a single parameter here, right? We don't really need u times u minus v times v. But there's a reason for doing that. That is an excellent question. Now I'm gonna give an answer to that just after the next slide.
Okay, thanks.
Yeah.
Why you need a difference of 2 Hadamard product? Why not you have use 1?
Yeah, that can be that comes with an easier answer because this term the u term only produces the positive components, and the v term only produces the negative components. Right? U times u is a non-negative vector, right?
Yeah, but some term of u could be 0, right?
Yeah.
It could also be sparse.
Yes, that's our goal, right? We want u to be sparse. And yes. Yes. Okay, so let's move forward, and I'm gonna come back to this issue a bit later. Okay, so the idea here is that it's okay that we have this objective function that has infinitely many global solutions, and not all of them are what we want, but perhaps only one or a few of them are what we want. The idea here is that while there are infinitely many solutions, if we design a particular optimization algorithm, right, that starts with a particular initial point and follows a particular designed steps, right, iterates, then it's going to convert to one of those global solutions, right? It's not going to convert to all of them. And the idea hence is that if we design the initialization and the iterations clever enough, then hopefully it's just going to give us the desired solution, right? And it's not going to convert to a undesired solution, right? So that's the idea. And it turns out this can be actually very easily achieved by a magic algorithm, which is the gradient descent algorithm that we all know about, right? With a little bit of the specifications, right? So one thing is that for these gradient descent steps, we need the initialization for ui and vi to be small enough. And the second thing is that for these 2 sets of optimization parameters, the theta, which is parameter of the neural network, and ui and vi, which are the new parameters that we introduced, we need to use 2 different step sizes for them in this gradient descent update steps. So that's all we need. And as long as we apply this, then I'm going to show some experimental results that our method is going to convert to the desired solutions. Okay. Okay, now coming back to the question of why having this specific complicated ugly form of u times u minus v times v, right? So here, I think I will not be able to provide a rigorous answer because that's gonna, takes a lot of, I'll need to talk into a lot of the details. But let me here to try to offer a kind of a simple explanation or the intuitions, right? So first of all, the first sentence here basically provide the background. So that is, there is a line of work that is saying basically that gradient descent is lazy in the sense that if you give it a small initialization, then it's gonna find you the one solution that has the minimum L2 norms, the minimum L2 norm, right? And this is for over-parameterized systems, right? If you have a system that has infinitely many solutions, then gradient descent is gonna give you the minimum L2 norm solution, right? But here, for the label noise problem, because L2 norm or minimum L2 norm solution is not what we want, right? And because label noise is sparse, we actually want to have L1 norm, right, to induce sparsity. And how do we get L1 norm from L2 norm? It's easy. We just need to use this relationship, right? And by using this relationship, the idea is that if my gradient descent is minimizing the L2 norm for U and V, then it is equivalent to minimizing the L1 norm of the S, right? Which is the variable to basically model the label noise. Okay, and here is basically a geometric picture for illustrating that. All that this picture is saying is that the unit L2 norm for the variable U is the same, at least in the first quadrant, as the unit L1 norm of this variable S. Right? So that's kind of the intuition here. Okay, so basically in short term, the reason we want to have this complicated form on the top is because that form is going to be needed for us to induce sparsity or L1 regularization on the label noise term.
And why do you need a difference of two terms?
Yeah, that's the question that Peng had, right? So because the U term only produces positive entries, right? It's a non-negative vector.
Okay.
And V only produces, V times V also produces non-negative entries, and subtracting them so that you can obtain both positive and negative entries.
S can be sparser than both U and V, or?
Okay, you're saying whether the support of U and V are going to overlap? Is that so? Because if the support of U and V do not overlap, then the sparsity of S is equal to the sparsity of U plus the sparsity of V, right?
Yeah. I mean, minimizing the two norm of U and V doesn't give U and V with sparse, doesn't give sparse U and V, but finally you want sparse S.
So basically, you're saying why is it not inducing sparsity on U and V individually? I think that's a good question, actually. Yeah, that's a good question. Yeah, maybe we can discuss offline. I think that's a good question. So, so basically here, by putting it in this form of U times V, U times U minus V times V, we get sparsity on the entire thing, right, on the S. So that's what we desire to achieve. Okay, any more questions? Okay, so now let's talk about the results, right? So here I'm comparing our methods with several other methods on the 710 and 100 datasets. And these datasets don't have realistic label noise, but what people do is to just inject some synthetically generated label noise. And there's various ways of injecting label noise. And the short story is that our method is better than the previous ones for all the cases. Okay,
I ask, so
Yeah.
I guess symmetric means that, whichever class you can flip the label to the others,
Yes.
asymmetric, but opposite, but is there any of these settings where if points are actually closer, there's a higher probability of flipping the label, or no, it's still totally uniform flip across the whole class?
That's a good question. So here there isn't. So here is only symmetric and asymmetric. But I believe the case that we're talking about also makes sense. It's a good test case. Yeah.
So you don't need any explicit regularizer on the U and V in your optimization.
No.
Since in your previous slide, it seems like you want to minimize the S1 form,
Yes.
L1 norm.
Yes.
But why is that left out of the objective?
That's a good question. The short answer is that if you add explicit regularization on the U and V terms, then this formulation is not going to work. Let's say you add upon this first term, you add the auto regularization on U and then another auto regularization on V, right? Then the solution you get is going to be U equals to V equals to 0. Right? Because that gives you, at least from a purely optimization perspective, right? Because that's going to give you a 0 objective value.
So how is the sparsity of the U minus V achieved if you don't have any explicit regularization?
That's the gist of the the method, right? So I'm not talking about this in this way because it could be a bit confusing. But the idea here is that deep neural networks themselves are not explicitly regularized, right? They are somehow implicitly regularized, but we don't have a precise categorization of the implicit regularization. And therefore, in order to enforce or bring robustness to these kind of systems, we cannot use explicit regularization on the noise. We should also be using implicit regularization on the noise term. And that is the gist of the method. That is why this is called double over-parameterization. So we need to over-parameterize. If we are over-parameterizing the signal part or the clean part, then we will also need to over-parameterize the sparse part, the noise part, and that's the gist of the method.
So is the idea here then the gradient descent is implicitly sparsifying the U minus V?
Yes, the idea here is to leverage the implicit bias of the gradient descent. Yes. All right, so I was saying that our method has high accuracy, and then the next slide is to show that our method is also fast. And so here I'm providing two versions of our method, the SOP and SOP plus. The story here is that the SOP is just applying our method on top of a standard training pipeline for cross-entropy loss. And the SOP plus is to say that in this community of label noise, people often adopt some other additional strong regularization to prevent overfitting. So here, in order to compete with the state-of-art methods, we have to adopt the same strong regularization so that we have a fair comparison with them. And adding those strong regularization makes our method slower, but still it's much, or at least faster than many of the previous methods.
I have a question about the overall loss function. I noticed you used the cross entropy loss.
Yeah.
But isn't by nature cross entropy loss are super confident that may just overfit on its own? Have you ever tried other kind of loss function like label smoothing or focal loss to see if it actually performs better?
That we haven't tried. And okay, so let me also mention here, right? So this is kind of a simplification. And if you do apply the method, at least for this label noise case, you kind of need to play around with the loss a little bit. So for updating the theta, you can still use the cross entropy loss. But for updating the U and V, you do need to have the squared loss. That's some detail that can be found in the paper. Yeah. All right, so the next slide is the result that I mostly want to show you is this result on this so-called Sabaten N dataset. So the story here is that we first developed our method and wrote a paper and submitted to SAML earlier this year. And then there was this clear paper that was made public, where they basically, created this new data set called Severton-N, with the idea being that, in the original Severton-N, there is no realistic label noise. And what they want to do is to say, oh, let's create some realistic ones to check whether these methods are really working or not, right, in realistic cases. And the way they do that is that they put the dataset online and ask 3 people to label the Severton dataset, relabel the training set. And these are the 3 labels: random 1, random 2, random 3. And so they make different noises in their labeling process. And then they also, conducted very extensive experiments, right, compared with a lot of the previous methods. And then what we do is that we just, took that data set and then apply our methods and do some tuning, right? And then this is the performance that we got, right? It turns out that our method is very good performing, right, and beats a lot of the previous representative methods. Okay, and not only so, if you look closer into some of the competing methods that are, also obtaining very good performance, they are arguably much more complicated than our method. Let's say for these 2 methods that also obtained good results, they are using this kind of 2 neural network based approach, where the idea is basically to train 2 neural network and hope that they don't make the same error so that they can help each other. And for our case, we only need 1 neural network. And then there is also this method that uses kind of a semi-supervised learning procedure where you need to iterate. Well, for our case, you don't really need to do all those kind of stuff. It's kind of a very simple approach.
For the clean one, you could still run your algorithm, right? Why here does it say not applicable?
Oh, yeah. So yeah, this is not updated. So this is kind of the first set of experiments that we, the first set of results we got. Now we have an updated version online now with all the results, also for clean data on there. Yes. Yeah.
All right. Can you explain again why the discrepant step sizes are needed? How do you choose those?
Oh, those are going to be hyperparameters that you need to tune.
Are you using optimizers with momentum as well, like Adam?
Yes. Not Adam, just the SVD with momentum.
Okay.
Yes.
How sensitive is it to the choice of alpha then?
It's very sensitive. You need to tune that.
Just to piggyback off that question, do you want alpha to be very small? Like, do you want the update for you to be slower, or like, or do you want updates for relative to theta, I guess?
Not necessarily. I wouldn't say we ask alpha to be small, large. Yeah, I forgot what's the alpha that we use, but by and large, you need to tune or find the sweet spot, right? It should neither be too large nor be too small. Okay, so so that's our method. And then to show you that our method is not only conceptually simple, hopefully, and also works well in practice, it also comes with theoretical guarantees, right? So here we did some theoretical analysis for our method. And to formulate or to set the stage for the analysis, right? What we should have been analyzing is this nonlinear neural network model, right, from the top. But that is a bit too complicated. So what we do instead is to analyze a simplified model where, instead of having a nonlinear neural network, we just work with this linear system, right? So here J is just a matrix, a underdetermined one, so that you have infinitely many solutions. And then again, the assumption on I star is that it's a sparse vector. And here for the theta star, we also need to make the additional assumption because, because the system is over-parameterized. There are infinitely many theta that is gonna satisfy this relationship. So what we do is to assume that, the one that we want to recover is the one that has the smallest L2 norm to make the problem well defined. And okay, so and then the algorithm that we are going to analyze is our method, that is, so this is just the rewriting or reapplying our methods to this linear system, right? So again, that what we're doing here is to introduce this U and V term, right? And then minimize the optimization problem on the top. And then the story is that we need to use this algorithm specifically designed with a particular choice of alpha between this for different parameters. And also for the initialization, we want them to be small for some small value of gamma. Okay, so that's the algorithm. And then the problem setup is for this algorithm, can we prove that the solution that it converts to recovers the the theta star and S star? Okay. Okay, and this is our result. So in short term, this is saying that under suitable choice of the parameter alpha and gamma, then you can, right, correctly recover theta star and S star, provided that this incoherent condition is satisfied, right? I hope this term incoherent condition is still familiar to you because that's the term we have mentioned. It's just that in this particular case, we need to specify the incoherent condition for this specific problem, right? So here, all that is required is that this incoherence or coherent measure, this mu j, is smaller than some quantity shown on the right. And how is this coherence measure mu defined? It's just like this, right? So here in the last line here, the U matrix is the column space of the J matrix, and the EI vector is the is the standard basis, basically a standard basis vector. So this is then defined as basically the inner product of that, and then take the R2 norm and then take the maximum. So yeah, so that's the.
I think I missed J. Can you go back to show me what is J?
Sure. So J is this variable in this linear equation.
Got it.
Yes. Okay, so but now, so this is incoherent condition is just expressed in a mathematical equation, right? So it's not very clear why it is called incoherent condition, right? And actually, there is a easy way to visualize that, right? So as what I'm doing here to visualize the quantity incoherence, the mu, right? So here I'm listing two cases. On the left case, the span of the U, which is the column space of the J matrix, is well separated from all the coordinate system, right? And in that case, you can easily check by the definition on the top left, you're going to get a small value of mu, right? So the coherence is small. And on the right-hand side, your U is well aligned with one of the coordinate axes. And in that case, again, you can check by definition, it's going to give you a large value of the coherence, right? And basically, the condition is going to be easier satisfied if you have small value of mu, which is basically saying that if you want to achieve correct recovery, right? What you want is that the span, the span of U here to be in some sense separated from the standard from the coordinate systems or from the coordinates, right? And the reason that we want to be separated from the coordinates because that's kind of the basis for sparse noise, right? In the sense that each sparse noise can be represented by a linear combination of a small number of the coordinate axes, right? So by and large, this incoherent condition is basically saying that the model part, right, the J should be well separated from the noise part. So that's the high level intuition here. Okay. All right. So I've talked about the application of our method on this task of robust image classification. And in the following, I have two more tasks that I'm gonna talk about very quickly. So it's just gonna be applying basically the same technique, but for two other applications. But we're gonna see that at least for the image recovery task, right? It's perhaps going to be a more interesting application because we're going to be able to see some, real images or, realistic images Okay, so let me let's start talking about the second work, which contains the next two applications. So this is a work done in 2 years ago, and this is my kind of pre-Google work. So in the following slide, you know, the material is not related to my work at Google. So this is work done with Zhihui Zhu and Qing here and Professor Ima at University at UC Berkeley. Okay. Okay, so the application of image recovery. So let's so it's just another application. So let's run through that quickly, right? So the task here is that we would like to recover a clean image from a corrupted image. And the method here is called the background method here is called the deep image prior. And the method works as follows, right? So what we do is that we take the input, which is the corrupted image, as the variable y, and then we minimize the L1 norm between this y and the output of a neural network that is going to be learned, right, with parameters theta. And here I'm picking the L1 norm because here I'm assuming that the corruption is a salt and pepper corruption or a sparse corruption. Okay, and this is, in case you haven't heard about this, right? So this is kind of a so-called untrained method in the sense that, the network never sees any other images. This corrupted input is the only image that it sees, right? It never sees any clean image. It never sees other images other than this plane. So this is the only image that it sees. And the idea of the method is to say that this neural network, if you design it properly, like in this kind of U-shaped convolutional neural network, then it encodes certain prior for clean images. And therefore, they are supposed to be generating clean images. Okay, so that's the idea. Okay. So at the end of the day, after this is trained, hopefully this F theta is going to give you a clean image. Now, here again, the essential concept is over-parameterization. And in this context, this is saying that the number of parameters in the DIP neural network is much more than the degree of freedom in the image that it's generating, which is basically saying that the network is too powerful that it's basically able to generate any image, right? Not necessarily the clean image, which we want it to generate, but potentially it could also generate corrupted images. And the consequence of over-parameterization is, again, overfitting, right? So here I'm showing the learning curve for this deep image prior, where the x-axis is the number of iterations, and the y-axis is the signal-to-noise ratio that measures the quality of the recovered image. And here the trend is that the performance first improves and then decreases. And what's happening here? So if we take a look at the picture that the network recovers at the highest point, then this is shown on the left, right? And this is a decently looking clean image, right? So, and in fact, this method works exactly by this early termination trick, right? So you have to stop the training at the appropriate point. But the argument here is that this is not really practical, right? Because in practice, you don't really know where to stop, right? The reason I can do it here is because I have that curve, and to plot that curve on the top, I need to have access to the ground truth clean image, right? Otherwise, I cannot plot that. Or right, so in practice, you cannot really use this, or at least it's not that straightforward to use this method to determine where to stop. And if you don't stop and train all the way until the end, then this is the image you are going to get, right? You're going to get kind of a very noisy image that is very close to the input, actually. So what do we do? So to just show you the results, right? What we are able to achieve is shown in this red curve, where our method don't really need early termination. Right? It's just gonna convert to a good solution. And how does our method work? So here again, we are applying basically the same trick, right, or the same method. Hopefully you can still recognize, right? All that we do is to introduce this new term, the GNH term, for the purpose of generating the corruptions, right? So here again, the idea is that the Y is my noisy environment, and this F theta produces the clean one, and this new term produces the noisy, the noise part, right? And then the idea is that we have to solve this optimization problem using a particular designed gradient descent with a appropriately chosen learning rate ratio alpha on the two sets of parameters. Right. So here the alpha is the ratio of the learning rate that you use for theta and for GNH, right? And so here, because we're interested in this application, kind of from a practical perspective, the benefit here is that this alpha, well, it is a tuning parameter, but in practice, you don't really need to tune that. And empirically, we found that alpha equals to 500 offers kind of a magical number that works well for all the cases that we tried. So you don't really need to tune the alpha parameter in practice. And so just to quickly show you some experiments, right? So this is the results that we obtained. So the leftmost figure is the input noisy image. You can see it's very noisy, right? And then the middle one is the result given by the DIP, which is the baseline. And the right figure is the result given by our method, right? So visually, perhaps the middle and the right figure, they are maybe kind of similar, right? But in terms of the SNR measure, our method is like 2 points better. But here again, let me emphasize, right? For the middle one, right? I'm actually helping their method to cheat by picking the one that gives you the best result, right? Well, for our method, you don't really need to do that. You can just train all the way until the end. And
I have a question. So for the middle method, you said you need like a validation. But for your method, you don't need that. You can just directly train it.
yes.
Yeah, so I guess that's just kind of puzzling. Like how do you yeah, like I feel like how do you evaluate this one? Do you just run it and then employ it directly? Is that the idea?
Yeah, I just run the algorithm. And for DIP, I'm just monitoring this curve. Or basically, I run the entire training, and then I just pick the image that is generated at this point. And for our method, we just run for this number of iterations and take the end result.
So it's just like the longer you run, the better. You don't need to do any validation.
No, you don't need. Yes.
Is there a comparison of like the time interval that both algorithms span? So like the actual term you add, does that like cost more computation?
That's a good question. We never measured that, but I'd say it's not gonna incur much computation cost because much of the computation is spent on training the neural network, right? Which is a deep architecture. So here it's just 2 additional parameters to train. I don't think it's gonna increase a lot of the training time.
There's maybe like more iterations that like compared to the other method.
You can see it here, right? Yeah, how do you compare? So for the DIP, the baseline, you can just terminate here, perhaps. But for our method, but even if you terminate here, right, our method is already offering a performance gain.
Thank you.
Yeah. Okay, so I also have 2 slides to show you. Basically, it's not a cherry-picked case, but for the interest of time, let's skip that. Because I do want to also mention the third application, which is the application of our method on the low-rank matrix recovery. And this application is interesting also because, low rankness is kind of a clean mathematical concept that we have studied extensively, right? And examining our method in the context of low-rank matrix recovery can offer some additional insights, right? Okay, so first of all, let's talk about this problem, right? So the problem is easy. So assume that we have a signal that is the low-rank matrix, but we don't really have access to that, but we only have access to Y, which is a corrupted version of the low-rank matrix. And the goal here is to recover the low-rank matrix from such a noisy measurement. So it's kind of a very classical problem. And there has been many methods that are developed for this problem, right? Perhaps many people here know about. Like the first one is the convex one, right? All we need to do is to penalize the nuclear norm of the X and then the L1 norm of S and solve this convex optimization problem. But the issue with such a convex approach is that it requires computing SVD in each iteration, which is very costly if your X is very large. And then there is these non-convex methods that were basically drawing a lot of attention recently, right? With the idea saying that, while non-convex problems are historically considered to be challenging, but it turns out that at least for some of the low-rank recovery problems, it's actually tractable and with provable guarantees, right? And this is it's kind of a non-convex method for this problem. And for this method, the drawback here is that you do need to know the rank of the X star, right, to specify the shape of the U matrix, right? But the rank is usually not known in practical applications, or at least it's a drawback of the method. So the idea here is that since over-parameterization or over-parameterized models are very interesting, right, or drawing a lot of interest, or have achieved great success, why don't we introduce over-parameterization to this low-rank recovery problem, right? And by saying that, I mean it can actually be seen from this non-convex formulation already, right? This non-convex method can already be viewed as a neural networks-based method. It's just that it's having a very shallow network, 2 layers, linear, U times U transpose, and that's it. And it is also a very narrow one because you are constraining the number of columns of U to be R, which is a small number, right? It's the rank. So the idea here is that why don't we over-parameterize? Let's not use a slim-shaped U. Let's use a square-shaped, right? As shown in the bottom case. And if that works out, right, this formulation in the bottom, then we don't have the drawback of the previous 2 methods, right? We don't need to apply SVD, and we don't really need to know the rank of the underlying X star, right? Because we're just using a square-shaped U. But the issue here is that this method of over-parameterization doesn't work as it is, right? At least from a purely optimization perspective, right? Because, so here again, the argument is that because it is over-parameterized, it's gonna be able to fit to any corruptions or any measurements. And hence our method here basically we are seeing this for the third time already, right? We are just applying the same method to this task where, in addition to the over-parameterization of the X term, we also introduce an over-parameterization of the S, the sparsity part, right? Hence the method called sparse double over-parameterization. Yeah.
Yeah, I'm conscious. So the iteration you're using 2 terms G and H is because you assume the Gaussian noise in there. Is it possible that if you extend, you use a bunch of G's and a bunch of H, that you can then at the end you're able to capture more variance of noise? In other words, the sampling style for this partially observed matrix can be extended to other various different sampling styles.
I'm not. So you're talking about other forms of corruption?
Yes, yes.
Yep.
Isn't you use 2 terms, one capture positive, one capture negative, because you have assumption on the Gaussian noise.
Yes.
But if you extend, instead of using 2 terms, you use more terms, 3 or 4, etc. Is that gonna maybe capture more other different noises?
More term, you mean adding upon here G and H add some other terms,
right?
In some other forms,
right?
I guess I have a follow-up. So I guess is this method robust to other different types of noise distributions, I guess?
Right.
Yeah, that's a good question. So yeah, I think these 2 questions are related, right? So throughout the talk, I've been talking about sparse corruptions, right? And because the corruption is sparse, we need this particular form of over-parameterization. But I believe the idea here is that if you have other form of corruption that has other properties, right, beyond sparsity, then perhaps what we should be doing is to design the appropriate form of over-parameterization for other types of noise, based on the prior on what the properties of noise, right? Yeah.
Thank you.
Okay, so I was talking about applying our double over-parameterization technique for this low-rank problem. So here, the story is the same as before, right? We need to have a particularly designed. I'll just finish in maybe three minutes. Okay, so the idea is that we need to have this particularly designed gradient descent algorithm with a discrepant learning rate, with a learning rate ratio alpha there, right, on the two sets of parameters. And here it's easy to examine the effect of parameter alpha, right? So here the x-axis is the parameter alpha, and the y-axis shows the recovery error, the low-rank error and the sparse error for the recovery of the low-rank and sparse components. The message here is that if you pick the alpha cleverly, then you can obtain simultaneously both low-rank recovery error and low sparse recovery error, right? But if you use another value of alpha, then the error could be large, right? So this is showing again that we have to choose the parameter alpha cleverly, right?
Can I ask something? So
Yes.
earlier when you showed, the bottom one with L1 and it doesn't work, you said the same intuition, it's over-parameterized. So we know there are many global optima, and there's gonna be one that like perfectly overfits the low-rank part or whatever.
Yes.
But we know that when that's a two norm, it does work, right? Because of implicit regularization.
Mm-hmm.
So but my understanding is like that's been proven just for gradient descent, like vanilla, without, because there's no extra term being introduced, and so there's no sort of adaptive way.
So are you talking about the noise least case, like the clean case?
No, with Gaussian additive noise and having implicit regularization. So like if you want to go back, I'm just talking about the last one.
This one?
Where U is n by n,
Mhm.
and then it's an L2 norm instead of L1. This one has been studied
Okay, so
for a few years now. It wasn't my work, so I may have gotten it wrong, but my understanding is just analyzing gradient descent, you can show
Yes.
because of implicit regularization,
Yes.
it recovers the.
Yes. So first of all, there is indeed this work on showing that, if there is no noise, right? If you have a what is that? Okay, if you have a low rank matrix without a noise, right, and you put it here, and then you solve this optimization problem, right, with the U and V, with the U transpose that are over-parameterized and now to norm. Then there are infinitely many solutions, but the U and V, the U is going to converge to a low rank solution. So that's
talking about like in a matrix completion, clean, exact matrix completion setting, right? But I thought there's also the result in the matrix recovery case where Y is this A times low rank plus noise.
Mm-hmm.
And you can also recover the low rank part.
For that, I'm not sure. I'm happy to learn the literature. Yeah.
I'll look again.
Yeah, thanks.
Yeah.
Yeah.
But anyway, if it was just gradient descent, so the difference in yours is that you are introducing a term and need this different learning rate for the new term. Is that sort of the contribution that I'm getting here?
Yeah, I'd say the critical part here is that we need to have we are gonna have the noise, right? And for the noise part, we need to have a separate additional over-parameterization term to model the noise part, in addition to the over-parameterization term that models the signal part.
Mm-hmm.
So that's the key idea here.
I see.
Yeah. Okay, so I have just one slide left, basically to rigorously show the effect of the parameter alpha in this case. And this is this result. It's kind of long, but by and large, what it's saying is that under certain conditions, right, the solution that the gradient descent with a discrepant learning rate, that gradient descent algorithm is going to converge to is the same as the solution to this convex optimization problem. Okay, and here it's also clear what the learning rate ratio controls. Basically, it controls the balance between the low rank regularization and the sparse regularization. Right, and so here is also the point where we are basically connecting, our method of double over-parameterization with this kind of classical approach of the convex optimization, right? And then from a practical perspective, there is the follow-up question of what alpha should I use? And for that question, there are already this kind of classical results saying somewhat surprisingly, right, that the optimal choice of the alpha does not really depend on the rank of the matrix or the sparsity of the corruption, right? It actually only depends on n, which is the size of the matrix, which you always know, right? And hence, basically, there is really no tuning parameter for this method. Okay, so that's all that I want to talk about, I believe. With that, I mean, just conclude very quickly, right? So at the beginning of the talk, I was saying that we have this kind of classical approach that is very good, right? But the unfortunate fact is that they don't work out of the box for over-parameterized models. And my main argument here is that that is no reason for throwing away all the lessons we have learned in the past 50 years, right? And we can try to revamp this kind of classical approaches. And it turns out that it's possible, right? And that leads to a method that is not only simple, that is not only probably correct, but also gives you very good empirical performance. Okay, so that's all I want to talk about. Sorry for going over.
It's a great talk. Any questions?
Yeah, so it seemed like both test curves having this monotonic rise. Do you think the theory your theory can explain, because it just seems very surprising, like very magical, why the test error the test accuracy, both test accuracy and the compression quality or the denoising quality, like seeing that monotonic rise, like how do you explain that? How is this able to do that?
Sorry, are you talking about this application?
Second part, the monotonically improving, like you can run your model for as long as you want and it will just keep getting better and better. Do you how does the theory, is there any theory that explains this very magical phenomenon? It just seems like it's really very good to be true.
Oh, for that,
yeah,
for that we don't. So we only have result for not for DIP case, right? But for the matrix factorization case, that at the convergent points, our method converges to the correct solution. But our results don't characterize the training procedure or the training dynamic, right? In the middle, whether it's converging, whether it's close to the optimal solution, that is not in our theorem. Yeah.
So it's like the intuition behind like why these algorithms are better than the existing ones because you're jointly trying to estimate the noise.
Yes.
Okay.
In an appropriate way, right? You have to over-parameterize the noise, right? In this way. So you have to model the noise basically. If it's sparse, then you need to over-parameterize the noise in this particular term. But if it's having some other properties, then you may need to have another form of over-parameterization. And
for these image recovery, I'm assuming you're adding like Gaussian noise to images and trying to.
No, I'm actually adding sparse noise to verify the effectiveness of the method.
It's a lot.
Yeah, it's a lot. Yes.
Okay. No.
Can you remind me of the sparse label noise model? Maybe after the front
again. Yeah, this one.
Oh yeah, maybe doing something to the previous.
For the previous.
So like the SI is the noise, right?
Yes. So the modeling is here, right? So this SI is the label noise.
Y is one hot for each eye.
Yes, Y is a one hot vector. Yes.
And SI is.
SI is the difference between the one hot corrupted label and the clean label.
Oh, sorry. So F is a simplex or one hot.
Oh, F is the output of the neural network.
After argmax or before?
After softmax. Yes.
Oh, after softmax, but before argmax.
Yes.
Okay.
Yes. Yeah.
I've run some experiments about the DIP plus over-parameterization.
Yes.
And it seems like it's not working when I use ADAM.
Yes.
Yeah, and if I use SGD, use gradient descent, it takes a very long time to converge, which makes the problem not practical.
Yes, that's a good point. So, okay, so what you're saying is that the method works only for gradient descent, but not for atom, and that is true. I believe for basically for all the work on implicit bias, right, or for the sort of implicit bias that we can characterize, we have to use gradient descent. And for atom, we're not sure about the implicit bias effect. So, and it's definitely going to be interesting to see whether these techniques of double over-parameterization can be generalized to using atom as well. Yeah.
Maybe just a different type of momentum that would be more compatible.
Perhaps, but I'm not sure. I guess it's going to be very challenging because nobody seems to have studied the implicit bias for atom. Yeah. Yeah.
So I think in John, like 2017, they showed like or maybe someone else showed like the noisy label are fit later.
Yes.
Like clean label get fit first. Like,
yes.
Do you know if your model has that property as well, or is it like something similar to that?
Yeah, that is basically the reason you can observe this trend, right? So it's the test curve first, test performance first increases and then drops, right? Which is showing that it's first learning the clean labels, or it's in fact, so a lot of methods that are using early stopping are relying on this kind of feature, right? Basically saying that the networks learn to fit both the clean part and the noisy part, but it fits the clean part much more faster than the noisy part. Yes, and you can also interpret our methods in that way as well. You can say that our method is first, fitting the clean part, but it's just in the form of introducing another variable to do this in a more principled way.
Can you tell me, so in the result that you have for the low rank or for the over-parameterized but linear matrix case?
Yes.
I was a little bit confused about how the incoherence was defined, like where that rank comes from. So, yeah, you need maybe just show it to me again.
Yes. Yeah. I went through this part very quickly. So basically, at the end of the day, we need to require that the rank of the J is small, right? So we have the rank here. We do need it to have a low rank.
Yeah, so if you go back just one, then where's the over-parameterization, or sorry, to this?
Yes.
Because you're saying J has more columns than rows, so.
Yes. Yeah.
So you need it to be, well, maybe not in practice, but you're saying it has to be exactly low rank, actually, even though it's a very wide matrix.
That's a good point. I think the exact low rankness is kind of a oversimplification, and I think what would make more sense is to study kind of the approximate low rank case where your singular values decays very rapidly. That will be a more reasonable result. But for here, we're just staying with the most simple case of assuming everything is ideal.
Yeah. I think something I hadn't thought of that I, think is super interesting from what you're saying is like that it is the incoherence notion that allows us to say things, and how can you talk about incoherence between something that's truly over-parameterized with something else that's truly over-parameterized, because they by definition can describe each other exactly, right?
Yes.
Because of the over-parameterization. So maybe finding like other ways to walk that line, except other than like exact low rank, kind of back to what the things our community knows really well, could be super interesting.
Definitely. Yeah, that's an excellent comment. Thanks. Yeah.
Any other questions? No, let's thank the speaker again.